you can actually note down, and I can give you another example, or you people can try another example theoretically. And similarly, it also happens in your microprocessor 8085. So please note down, especially the carry flag part, so that your understanding becomes better. So you can either note down this, and then you can do any parallel 8-bit number and do addition and then subtraction, and then you will be able to appreciate this more. So please note down. And some of you please say yes or hello, otherwise I feel I am kind of disconnected.
Yes, sir. Yes, sir.
Or the internet has gone or something like that. So I really do not know what has happened. So I have to actually ask you whether you are still available or not.
All right, sir.
Yeah, just okay would do. I mean, like, thanks a lot. Yeah, so please copy it down, and the moment you finish, yeah. You can also try another 8-bit number. Somebody says, just give me any 8-bit number. So first of all, before we move further, this is all. Let's talk a few 8-bit numbers. Try to convert into its binary form. Let's take, let's subtract 8 for say 9 from 8, and let's subtract 8 from 9. So we do an addition of 9 plus 8, and we do a subtraction of 8 minus 9. So all of you please perform that, and then you will be able to appreciate it better. Manali Manali, are you there? Badal?
Yes, sir.
Okay, so did you just copy it? Are you? I hope all of you are having a notebook.
Yes, sir. Yes.
Yeah. So you can copy down this, as well as you can actually perform a simple addition and subtraction. In the addition, you need to add two numbers having value of 9 and 8, convert into binary form and perform the addition. Then you perform subtraction, 8 minus 9 in the binary form. So by the way, what is the, can you see this number? All of you?
So, yes, sir.
What is its equivalent form in decimal and in hexadecimal? This one and this one, and the result? Any volunteers? This one, and this one. Similarly, this one, and this one.
But it's 181 in decimal.
This one is 181.
Yes, sir.
And this one, all of you, those who have just, I don't want only one person to be representative of the whole class. It's
108.
just sorry. This internet it keeps popping. Huh?
108.
108. So 188. 1 plus 108. It's yeah. So any other volunteers? What is this number? Any other volunteers? Not the same person all the time. So why I have asked you this specifically, because this is a 8-bit number. So what is this? What is the sum total?
So 289.
Huh?
289.
289. Okay, fine. So here, this is going beyond this. So you have an extra carry here. Okay, similarly, if you have another one which is reflected on the 5th bit, then your carry auxiliary carry flag gets affected. Otherwise, this carry flag gets affected. Similarly is the case when you're doing a simple subtraction. Which is what is shown here. You can take any other example as your homework, and I think all such things which I'm asking you to do is a part and parcel of your assignment. Or so I will be coming out with a first assignment very soon, in which I will be already asking you questions that I have asked or discussed in the class itself. How about this? What is this result? Ram Mohan, Ram Mohan, Daksh, Daksh Kumar.
Yes sir, yes sir.
Okay,
सर ब्लैक स्क्रीन आ रही है अभी, दिख नहीं रहा. एक सेकंड.
so I'm actually talking about this. Am I
सर
audible?
minus 233 is it?
So what is this number?
So minus 233.
No. What are we subtracting from what? What is there? What is this number?
So 181.
And then what is this?
So let me calculate.
So it is 181 minus What number?
204.
So what should be the, if you do a simple subtraction, what should be the answer?
Sir, minus 16.
Okay. So what is that you're getting here? In other words, how do you perform your subtraction? Again, this must have been taught to you in your previous class. Simple addition, simple subtraction. The moment you were introduced to half adder, full adder, subtractor, so there are digital circuits inside your digital logic which are performing all these operations. Here we are talking in particular about 8-bit. So if you do it in any form, whether it's hexadecimal, whether you do it in binary form, or whether you do it in a decimal form, the answer should be always same or not?
Yes, sir, it should be.
So that's another way to cross verify. I mean, like suppose you're having a number in binary form or even in hexa form or any other form. Did you do BCD before? Have you ever heard about binary coded decimal BCD? Hello? Manas?
Yes, sir.
Have you done BCD before? As in like previous classes? Binary coded decimal?
BCD adder, yes, we have done BCD adder.
Okay. There is a disturbance. Please switch off your mic. So I think once you have noted down this, you just try to do simple subtraction of few numbers. I think I will also give you as a assignment in your in near future. And once you perform all those simple subtraction or addition or something like a BCD counter, you will be able to appreciate more. So when we are talking about this auxiliary carry, it is reflected in your bit 3 as I was mentioning. So 0, 1, 2, 3. So this would be reflected further on. So it is talking about this part. And when you're talking about simple carry, then it is reflected on your this bit. Okay, so this is what or your 7th bit. The parity flag when we are talking about even is put to set, and if it is odd it is cleared. So basically again these are terminologies that you're using for zeros and one. Okay. So now we just go a bit further. I think I will give you some assignments to perform addition, subtraction, and so on and so forth. So within the internal architecture of your 8085 microprocessor, it generally consists of your general purpose registers, the accumulator, and the flags. Beyond this, it constitutes of your program counter. So please note down about this. This is very important and critical. So what is a program counter and what does it do? So the program counter is a type of register which is used to control the sequence of execution of instructions. So this is how the whole processor generally works. It is working as the instructions are getting executed by the ALU of your CPU system. So the registers which are inside your CPU system holds the address of the next instruction. So always remember, the execution of the instructions is done, or it all started by execution in a sequential form, and it is done one after another. So suppose you as we had already talked before, that our memory was kind of divided into many subdomains, having RAM1, RAM2, RAM3, RAM4. So in any of these subdivided RAM, one can have sequence of instructions that the ALU or within your CPU needs to follow. So ALU is basically your arithmetic and logical operation, and within this, it is within the CPU, which also constitutes of your control unit as well as your general purpose registers. Remember, the address is always 16-bit wide. I don't know why it's here. Then we also talk of the stack pointer. So what is a stack pointer? Stack pointer actually points to the 16-bit register that is used to point into the RAM memory. Remember, the address of the data which you want to retrieve from your RAM is of 16-bit, and the data itself is only of 8 bits. So the memory, generally when we are talking about memory, we are talking about this RAM memory. Okay, so the memory of this register points to a special area called the stack, and the stack is the area of memory used to hold the data that will be retrieved at a very short notice. This stack is used to access in a last in, first out fashion. So the approach is like whatever comes, it gets stacked into your stack memory, and depending upon its arrival, there is a sequence that happens, and it follows a fashion of retrieval and operation, which is last in, first out type. I don't know why is it going back to this thing again and again. So please note down about these two things: stack pointer and program counter. Are you students there? Am I still connected?
Yes, sir.
Okay. So program counter is something which we have talked in detail, as well as your stack pointer. The other thing is talking about the other types of register, which is non-programmable register. So instruction is stored in your instruction register after being fetched by the processor. Okay, and the decoder decodes the instruction in your instruction
Of different options here to look at.
They're
and
the
we'll go
multiplex
through
ones.
each one of them.
Yeah, so what
We've got a cool
pin
feature
numbers are we
here to
referring to in the
convert
pin diagram?
the
These are
shapes
pin
that
number.
we draw into
So wait,
proper
let me check
shapes.
it out.
If you really screw up and want to start over, they don't mind as long as it connects properly. So you can see that it converted the
These are
horrible square I
0
did
to
into
7.
a perfect square.
0 to
And
7.
if I was right now, I seem to be on a
So the
roll like
pin numbers
boss.
are 12 to
So that's
19.
pretty awesome. And then this
Okay,
is where I
okay,
screw up.
okay,
Murphy's Law. Yep. Anyway, there are
How about
some
the rest of the class? Are
multicolored
you able
pens
to
that
go back to our previous pin diagram? We are actually referring to this one. Sorry. Yeah, sorry. This diagram. So we are talking about pin number 12 to pin number 19. So this is acting. These are the pins from which both your lower order address as well as the data from your RAM that would be communicated. While your pin number 21 to 28 would be sending the higher order signals of your address. Class, is this clear? Are you there?
Yes, sir.
Right. So bits AD0 to AD7, which is 12 to 19, from pins 12 to 19 are bidirectional and serve as communication of a lower order address A0 to A7 as well as data D0 to D7.
Sir, is this fixed?
This is fixed. This is fixed. So this
Why,
was,
sir?
huh? Yeah, what is the question? Why is it fixed?
सर ये लोअर और हायर पहले से फिक्स कर रखे हैं या फिर सर कैसे?
हाँ, so it is a
इन पिन नंबर सर इन पिन नंबर्स को ही हायर दिया गया और इन पिन नंबर्स को भी लोअर दिया गया.
हाँ, तो ये है कि when that is what a kind of engineer does. So basically there is some company, so they fix कि it's like, you know, in India you have right hand drive, and in some of the other countries you have a left hand drive. So these are defined by the engineers who are coming out or the government who are giving some convention. So as the government comes up with certain conventions, similarly the engineers also come up with some conventions. So they just decided, they were the pioneers of the microprocessor, and they just decided, okay, let's have from 12 to 19 as pins which are sending your data. That is not actually too much relevant. What is relevant is the capacity. The capacity that we are talking about is 8-bit period. And when they are talking about the same time, it is multiplex time shared. So means that they are not exactly at the same time, but they are under the time shared rule. So that means either of the two. You cannot have both the data going exactly at the same very time. Okay.
Okay, sir.
So that is a convention. Now you can, if you want to design your own microprocessor as an engineer, or say a 8085. Remember, we are talking about late 1970s. So that was 8085 microprocessor was the latest technology at that stage, like at our grandfather's stage. So that was something which was like the latest technology. So Intel came up with this, and this was just a convention. The important thing was that it was 8-bit microprocessor. That means the communication of your data or your addresses could only happen 8-bit at a time. So as I already mentioned, AD0 to AD7 are serving as a dual purpose that are demultiplex to get the information. So multiplex and demultiplex to get the information in the form of the lower order address and the data. So it was used both to send and retrieve the complete lower order address and the data. So for retrieving the data, you need the whole 18-bit address. So the lower order 8-bit address plus your higher order 8-bit address would make the full address, would make the full 16-bit address. Only once you know the whole complete 16-bit address, you can retrieve the data. So the higher order bits of the address remains on the bus for the 3 clock period. So this is how the actual operation within the ALU system happens. In this, the lower order bits only remains for 1 clock period, while the higher order bits of the address remains for 3 clock periods. So if it is, this is for higher order, the lower order, since it's only for 1 clock period, it also needs to be made sure that it is not lost in any manner. It does not, the processor does not lose the lower bits in any manner. Okay, so for this, the usage of external latch. Now this latch again is going back to your previous knowledge in your previous class, one needs to have the whole entire address for the full 3 clock cycles, and for this reason there is an external latch that is used to save the value AD0 to AD7 whenever we are talking about the address, which is 16-bit. Okay, and to trigger on the functionality of this external latch, one needs a ALE system. So ALE basically is your latch enabler. Latch enabler. Is that clear, class? So this is how.
Yes, sir.
Okay. So you may just note down this. This is your 8085 microprocessor or your ALU system. You have higher order addresses A8 to A15, which is directly having communication with your external RAM. Then you have the other 8 bits, which is AD0 to AD7. It is bifurcated into 2. One is only talking about your data D0 to D7, and using this latch, it is talking about the lower order of your addresses. And this latch is enabled by your ALE system or your latch enabler. So in this, how does this part operates? Is your ALE operates as your pulse, because we are talking about 3 clock pulse and 1 clock pulse. Remember? So ALE operates as the pulse during your first clock pulse will send a signal to enable your latch and able to extract the lower order of your address. Then when your ALE goes in a dormant state or the low state, the address is saved and AD0 to AD7 lines can be used as a data line. So here, between communication between here and here, you have a difference of 2 clock pulse, and it is synchronized by the latch and the ALE system. So difference between this and this is for 2 clock pulse. Is it clear? Manali? Daksh?
Yes, sir.
Yes, sir. Clear.
So expanding on this demultiplexing concept, um, the higher order address is placed on the address bus and it holds for 3 clock periods or 3 clock pulse. The lower address is lost after first clock pulse, and this address needs to be held, which is actually achieved by using a latch. The address AD0 to AD7 is connected as the inputs for latch. So the latch chip is 74LS373, and the ALE signal is connected to enable the G pin of the latch, and the output control of the latch is grounded. So you can just note down, maybe this can be how the internal operation of the communication of your 16-bit address and 8-bit data. This is to explain and expand on that, and talking in terms of how much clocks is required for the communication and the retention time of the lower and higher order of your address signals through your address buses. Am I audible? Hello?
Yes, sir.
Okay.
Yes, sir. Yes.
So please note down this before we move further. I think this diagram is very important. Please note down. This is very important to understand the basic operation within the CPU system. So when this pointer is pointing to the particular address or the data in that particular address of an external memory element, which is generally a kind of a RAM. Remember the RAMs, as of now there are two predominant RAM system. One is your DRAM and the other one is your SRAM. So dynamic random access memory and the static random access memory. Again, these DRAMs and SRAM is made up of basic transistors. But they have other components too. So can we move further, class?
Yes, sir.
Yes, sir.
Okay. So this is your overall picture. So you may also draw this. This would help you to correlate with your 8085 transistor and your external memory chip. So this is input output memory, this is read statement, this is write statement, which is connected to the read write. So these are internals. So this is your CS, which is your chip selection within your circuit, and we have already talked about the internal memory of your 8085 microprocessor, which is having a total capacity of 64K. All of you, please note down this. This is giving you the complete picture.
Okay, sir.
So I stay outside the campus. I'm not having an access to your writing pad. Hopefully, whenever I go next to within JNU campus, I will try to get the writing digital writing pad. Hopefully, I can also write down while I'm taking the class, and probably but one cannot replace the blackboard and the PPT thing, which is there. So I hope I can do justice on this online mode. I will give you some of the references and some of the other study materials through your Google Classroom shortly, along with some assignments, so that things become much better and much more clearer for you students. So I think you, as a student, you also need to brush up with your previous knowledge, as well as perform all kind of assignments to, understand things better. As far as lab components are concerned, I really do not know when exactly is your university
Add labs. Yeah.
you sit in the lab and perform any kind of experiment. Has it already started or not yet?
Not yet, sir.
Not yet. Yeah. So this course has a strong element of lab component. Basically, you can actually see the whole microprocessor kit, both 8085 and 8086. I think beyond that, I may not be doing, or there hardly any time. This itself will consume a lot of time because it's something which is very new to you, and has all kind of digital blocks and all kind of programming language at low level, which is like assembly language programming. So understanding this itself will take some good time, and you're talking about two different generations of microprocessor. But then all the new microprocessors that have come up are the extension of your x86 microprocessor architecture. So this gives you a good ground to kind of step further if you are further interested in VLSI architecture or computer architecture or something like that. So there are courses in computer architecture, if you see, in your CSE department. So I think that should also be there in your EC part. So it comes under the umbrella of ECE only, or VLSI only, VLSI and stuff like that. So can we move further? Are you done?
Yes, sir.
So what is chip selection circuit? What is selection circuit?
Yeah, so basically within this, if you want to talk of particular domain within this chip, which is a memory chip, here it is talking about 1K. It is not actually 1K. In your 8085, we are talking about the total capacity as 64K, and we have already talked in terms of that RAM memory being mapped or divided into various domains, having RAM 1, RAM 2, RAM 3, RAM 4. So the first question you should ask is, why do we need to kind of divide it? Anybody? Anybody? Why do we need to divide RAM?
To make retrieval of data easy.
Retrieval of data easy. Okay, further.
So to enable fast communication between microprocessor and RAM.
Isn't it the same thing the previous? Why do we need to? I mean, like, what are we doing actually?
So as we are moving towards the higher level, we are decreasing the size.
I didn't catch that. Why do we need to have? So this is a RAM. This part is a RAM. Forget the 1K byte, but suppose this is the external memory. Okay, let's go to the memory mapping here. Okay, why did we have to kind of? Why couldn't we have one RAM? Why they have kind of divided into RAM 1, RAM 2, RAM 3, RAM 4? Any idea, or is it just because they felt like let us do it, and so they did it because they were pioneers and nobody had to question? I think the first thing a science or engineering graduate should be doing is questioning why it's happening. What is the reason? If you give a very generic answer, okay, to make things better, that's you're just using an adjective.
So we usually segment that because you told that, we want raw data, instructions, and result in different RAMs to be stored.
I couldn't understand. I think your voice is not clear.
Sir, it is segmented as we want raw data, instructions, and the results
Correct. So I think what they want is not to mix up. So the instructions, the raw data, and the results. So some and the other things that are required in the overall operation of your CPU. Suppose you want to do 2 addition, and it's in it is say so this is the 16-bit equivalence of your address, and within this, say from 4400 to say 5FFF, so like 4401, you have a 8-bit data, and then 4402 you have another 8-bit data. Okay, and you want to do a simple addition. So the instruction for addition is, suppose in this RAM 2 from say 6000 to 8FF, it would help you because you have all types of instruction like addition, subtraction, multiplication, doing OR, and all kind of arithmetic, logical, and other different types of operation, which we will be talking at a later stage. Okay, they can be separated from your raw data, and and then if you have performed, say, in your external in your CPU system, after the performance of all these arithmetic and operation, you wouldn't like to mix it either with your instructions or sets, or with your raw data. You would like to I think store it some other place, say in RAM 3 or RAM 4, and then there will be another some kind of a mini segmentation to so that you have no mix-up, so that retrieval is fast as well as access is fast. Okay, so this is one of the, this is where your chipset selection also comes into picture. So it will be directly linking to the, sorry, just a moment. Yeah, so this is where your chip selection circuit would come into picture. This chip selection circuit would enable you to identify which of the various blocks of your memory segmentation one would like to go directly, so that you have faster access of reading and writing into the memory. Is that clear?
Yes, sir. And sir, this another question: MEMR and MEMW, which we have in the separate blocks.
Yes, so that is memory reading and memory writing. That is enabled by this read and write statement, and these are your input output for your memory. So MEMR is like memory read, memory write.
Okay, sir.
So this is generally a memory, and what you're doing is, again, as I mean, like the generic term is to have faster access. Faster access. Then whatever happens is within your ALU. All kind of operation is only happening in your ALU. What is this memory used for? It is either for storing your instructions, like we will just see in the in our classes, in our future classes. What are those instructions? That can be simple addition, that can be simple division, that can be some kind of floating point, this thing. That can also have, like, whether you have so 8-bit would be only result, whether it's kind of positive or negative, whether it's having any sign or not, whether it's having any carry or not. So all those things we would not like to get mixed up in your 8-bit answer. Similarly, all your instruction is identified by your 8-bit binary form. We will just see in the near future. Add is an add operation has an equivalence 8-bit binary form. That is what these engineers or the scientists in these big companies kind of identified with, and they kept it. So the equivalence, when they just gave it to your microprocessor, that kind of instruction was performed, and this is what we will be learning it. That is why I say machine only understand zeros and ones, and zeros and ones are the reflection of your transistors in zeros and one stage, and that is only when you are talking about digital electronics, because it's only talking about the on state and the off state. So everything is, so basically when we say zeros and one, that means the transistors, the equivalent transistors are going in on and off states. Period. So is this clear?
Yes, sir.
So you got what do you mean by chip selection and the concept of your memory read and memory write. So memory read and memory write is what? So suppose you want to retrieve your data from here. So what you will be doing? You will be reading into from a particular memory address. So like we had bifurcated the whole memory in, and we had segmented the memory having different into RAM 1, RAM 2, RAM 3, RAM 4, particularly for this 8085 microprocessor. And that address was defined, say from something something to something something, which was 16-bit address. Okay. So this chip selection circuit would, ask you to to go to that particular memory address in a faster and most efficient form. To probably get the raw data, say like in 4042 or 4044 memory address.
Yes, sir.
Okay. Any other questions?
No, sir.
So now we go to the instructions, 8085 instructions set. So what kind of instructions that one would be giving? I think let's start with this, and I think it's almost going to be like 12:30. So what instructions is again would be stored in a particular memory segmentation, because it will help in your faster retrieval and reading, retrieval and execution of your various instructions. Remember, the processor speed was very slow that time, and that time that computers that we are talking about were not as small as your smartphones. Those processors were huge. Remember, it was not only in terms of the sizes of the, it was not only in terms of the processing power of your microprocessor that you were using in your computer. I think within your JNU campus, in your computer science department, above your floor, there's this auditorium. People say that they used to have a huge computer in that space way back in the 70s and 80s. So it used to occupy huge space, and that was the case all over the globe. Okay, so initial computer used to not only have very low computing power, which was of the order of megahertz, but also used to occupy huge space, basically because your transistors were big, your circuits were not so much optimized. Your circuits were very raw in nature. So as time has progressed, you have circuit designers who are coming out with better circuits, as well as you are having better transistors and better architectures and so on and so forth. But at that time, it was just raw. And when we are talking about these 8085, they were nothing like an operating system. We will just directly talk. We were writing codes directly to the machine in form of your assembly language program, and that is what we're going to be introducing here. So there was no compiler, there was no. Have you heard about this compiler and operating system class? Class?
In what context?
Yes, sir.
In the present context.
Yes, sir. Yes, sir.
Yes, we have, but like.
Yes, sir, we heard.
So all your whatever you're doing, when you're using a smartphone, it is having what? It is having when we say Android. Oh, okay, let's talk about the simplest one. Microsoft. What does Microsoft do? I mean, just take 1 to 2 minutes. What does Microsoft do? It is essentially,
Sir, an operating system.
yeah, Microsoft basically is giving your operating system. Similarly, it's with your if you're having, say, so that is for majority of these laptops and desktop. The others is like your Linux operating system or by Apple, both as desktop, laptop, palm top, smartphones, so on and so forth.
Yes, sir.
Okay, but this was not existing way back in 8085 times. That time these concepts did not develop, but still people were using computers. So at that time, these computers were at a very nascent stage, which used to occupy huge space, which did not actually use some kind of architecture, which were using you know, the lowest, the low level language, and that's it. And as time progressed, a lot of development has happened. Now we are talking even in terms of your apps. Okay, so this is going back to the time when it all started, so as to make you understand how it all built up. Because the assembly language thing is still on, but that has now many layers, and now you have so many different types of high level language, including Python and C and stuff like that. They are again converted back into your assembly language, and which is what your machine understands. So machine only understands low level language. It doesn't understand anything else other than that. So going back to 8085 instructions. So this is the 8085 specific instructions that we will be talking about. Again, as somebody did mention, why have we divided or segmented our memory is so that these instructions are at separate region, the raw data is at separate region, so that there is no mix up, there is no corruption of data. Am I audible? 5 is a 8-bit. It can have a maximum of 2 to the power 8 instructions. So it is talking about the maximum capacity. Can have 2 to the power 8 or 256 instructions. So the combinations of this actually, so that is the maximum capacity, but one can have or one can use these 246 combination representing only 74 instructions for your 8085 microprocessor. So these instructions can be grouped into 5 different group sets. Please note down, now we have already started to talk in terms of instruction that the microprocessor system, that is the ALU system, would be executing. So your CPU system basically has 3 major functions. So it retrieves either data or your instructions. Then it decodes, and finally it executes. Retrieve, decode, and execute. And this cycle continues till all your instructions within the CPU are executed in a sequential manner. So what are the types of instructions? It has been classified or grouped into 5 different formats, groups. The first one being the data transfer operations.
Yes, sir.
Second one is the arithmetic operations. The third one being the logical operations. Fourth one being the branch operations. And the fifth one being the machine control operation. So remember, we are only talking about 8085 instruction. So as time involved, the number of instructions as well as the size of instruction also increase.
Sir, what kind of instructions would branch operations have exactly?
We will be talking about that in detail in our
Alright.
yeah. We will be talking in detail of each and every operation, whether it's equivalent, hexadecimal form, and the and binary form. I think there are hardly 2 minutes that is left. So should we just start with the data transfer operation? I think that would just help. We can start again. So before we get into that, I think you should also note down, because you're probably coming for across these things for the very first time. Please note down. So the instructions and your data formats. So each instruction has two forms. The first is the task or the operation to be performed. This is called your opcode or your operational code. But please note down this, these are very important concepts, and we will be building up upon this. The second part is your data itself to be operated upon, and we call them as operand. So opcode and operand. So in case your lab doesn't start, I think we will also see if there are some types of simulator that you can actually download, and once you have gone through the initial classes, you can actually start to implement them on those downloaded 8085 simulators, and once you execute them, you will be able to appreciate it further. So first we will be giving you assignments, then I will ask you to probably start using those simulators, which will further help the cause. But if we are lucky, and if we are all lucky, we may have lab sessions and you can actually do the same thing on a kit. That will give you a better understanding and probably a very good feeling of what you're doing. Remember, way back in late 1970s, this was the latest technologies for performing all kind of operation. This is what was actually being used.
Sir, how would one use this for like a moon landing and stuff though?
Huh?
How would one use this for a moon landing? Because that's also when the moon landing happened in 1968, right?
1968, there was Intel did not come into picture. So the first chip they came was in 1971, 4004, and that they used for a simple. So at that time, in your space technology, they were not using any processor. Now,
So how
now,
did they manage without a processor exactly?
huh?
How did they manage everything without a processor?
Well, how did they manage? They manage without a processor. That is kind of a non-automated system. I mean, like so, like just for example, you have cars. You just talk about 20 years back, or maybe beyond that, like all those. Or even if even if you are going to some places like Kolkata, I know of places like Kolkata or even Mumbai. I do not know much about Delhi, whether they are presently. There is this black and yellow taxi, and those are like some ambassador cars. So they are as raw as possible. They do not have any kind of a electronics chipset. But as time has progressed, all these cars are having a lot of these different types of electronics integrated into it, and the future is definitely beyond that. Future is like electric cars and probably governed by AI and all. So that would be fully electronics based cars. I mean, like if you see some of the electronics companies like Tesla and Sony are coming out, so the past and the future is very different.
Yes, sir.
Past was so like all your past cars or even the present cars are based on gasoline. The future may not be anyway dependent on gasoline cars. Gasoline and the so similarly for your space research, I mean, like previously they were not using any kind of electronics in that. Now everything is guided by the IT. IT as in like the chips and the related software. To
Right,
make
yeah.
to make a chip itself, you need software. Why you need it is because things are very complicated. So instead of making a prototype every time and keep on improving would take a lot of and seeing the output would you would need a lot of investment. So the best thing is simulate it. So if you simulate it, you don't need that hardware to be done again and again to improve and see the results of your improved version. So you see it through. So once you're convinced with your software that you are able to get better performance, then you translate into a real chip. And then once you get the real chip, you would finally authenticate your simulated results, and then you can start to use it for your space application, for your defense application, for your commercial application, for your medical application, for your anything. So all these design tools and simulators generally they use is one reason is that things have become very complicated, so it will take a lot of manpower time. Secondly, it will help you to reduce the cost. As I mentioned, I think previously also there's one or two industries. I mean, like generally they give a very the economists give a very sweeping statement that as time has progressed, what you have seen is inflation all over, which is not actually the case. The whole IT industry, the cost has always gone down, deflation. But nobody wants to talk it because that's not a catchy word. Similarly, in automobile sector also, you don't see that kind of inflation. As time has progressed, the cost has invariably gone down, whether it's solar cells, whether it's any kind of electronic goods, whether it's kind of any kind of cars and all. You see more and more sophisticated thing, but the price is not getting inflated by, say, with respect to your rate of inflation, which is around 6%, 4 to 6%. For the rest of the things, that is the case. So this is where, so cutting cost in it's not only in terms of making much more powerful processors. It's also in terms of making it more efficient in terms. So technical improvement would be making it more powerful, getting rid of the latency issues, making it faster, longevity and reliability of your chips, as well as the overall cost of the chips. So there may be 5 to 10 parameters for any chip where engineers all across the globe are trying to improve. And then you talk about improvement in terms of its operating system, compilers, everything every time is getting improved. So when the iPhone or Samsung come up with the latest technology, they come up with this operating system, the chip technology, the RAMs, their processors, their everything, whatever they can improve in their next generation. But at that time, they were hardly there. Now, they are full institutes. Even ISRO has SCL Chandigarh, and I think there is SAC in Ahmedabad. So they make chips. The rest of the information they keep confidential. Yes. Any other thing?
No, sir, none.
Thank you. We shall start from.
Good afternoon, sir.
Thank you all, Daksh, Manali. Manali, you're there? Manas?
Yes, sir. Yes, sir.
Premlata? Premlata is not there.
Yes, sir.
Okay, you're there? Good. Okay, thank you.
Okay, sir. Thank you.
Thank you, sir. Thank you, sir.